So we're going to do a few more problems from section 8. Then we're going to move on to chapter 9. So the test is next Tuesday. I'll let you know what it's on. It's on chapter 8, but I'm not sure how far I'm going to go as far as just having enough time for you guys to get finished. So it may not be the entire chapter 8. So section 8 was dealing with integrals where one of the limits was infinity, or where one of the limits was where the function went to infinity. So we're going to look at this case of the cube root of x, where we're going to integrate from 0, where the function goes to infinity, to 1, and then we're going to integrate from 1 to infinity. So they're both cases, and just based on what I mentioned previously, if you look at the function 1 over x, the cube root of x, you'll see that it approaches the y-axis pretty quickly, but it doesn't approach the x-axis very quickly. So our intuition would be that the integral, the red integral, which is the one from 1 to infinity, would be undefined, and the one from 0 to 1 would be defined. It'll turn out that's true, but let's just go through the steps. So if you didn't turn in your assignment the thing we did in class on Friday, and you were here Friday, you can turn it in today. If you weren't here Friday, I've given you a copy, and you can turn that in tomorrow. So the first one we're going to look at is this one. So what we'll do is we'll replace the limit where the function goes to infinity with this dummy variable b. And that's not right. It's to 0. And we're approaching it from the positive side. So we integrate from b to 1 of 1 over the cube root of x dx. So the first thing we do is we'll change the expression inside the integral into a fractional exponent. So that'll be x to the minus 1/3 power dx. And then we integrate. This is a definite integral because we have limits. So we'll get x to the positive 2/3 divided by 2/3 evaluated between b and 1. And then we plug in the limits. So this 2/3 will become 3/2, so we'll get 3/2 times 1 to the 2/3 minus b to the 2/3. And then we take the limit as b goes to 0. Now, remember, when you have a one-sided limit like this, it's just like a normal limit. The only difference was, I'm trying to think back to our flow chart. Yeah, I mean, there wasn't really that much difference between the two. So even though it says from the positive side, if you can plug in 0 and have the function be determinant, then you can just evaluate it at that value, even though it's coming from just one particular side. So when you plug 0 in for b, you'll end up with 3/2 times 1 minus 0 to the 2/3, which 0 to the 2/3 is just 0. So you end up with 3/2. So the answer is 3/2. The area underneath the black curve is 3/2. And that's because this function approaches the y-axis quickly enough such that this little sliver of area, when added up all the way to infinity, is a finite number, not an infinite number. So the only thing we do differently in the second part is we have the dummy variable b be the upper limit. So let's do that. And also the b, we're going to take the limit as b goes to infinity instead of when b goes to 0. So the second integral will be the limit as b goes to infinity, integral from 1 to b of 1 over the square root, cube root of x dx. And because the integral is the same, we can come down to this part. We're going to skip that second step and just say it's the limit as b goes to infinity of x to the 2/3 divided by 2/3 evaluated between 1 and b. Because again, I'm replacing the limit that is infinity by b and then taking the limit as b goes to infinity. So that'll end up being 3/2 times, oops, I left a step out here. So we still haven't taken the limit yet. So we're going to evaluate the limit at the upper limit, evaluate the integral at the upper limit. So I'm going to bring the 3/2 out, and we'll have b to the 2/3 minus 1 to the 2/3. So the lower limit is finite, but when we plug in b equals infinity, you'll see I get b to the infinity to 3/2, which is infinity. Okay, so when you plug in infinity, you get 3/2 times infinity to the 2/3 minus 1 to the 2/3, which equals infinity. Therefore, the integral is undefined because it's big. Let's divide, obviously. You take infinity to any number, you're going to end up with infinity. Okay, so again, that agrees with what we thought was going to happen. Okay, so that's it. We're going to skip that one because it's pretty much the same as what I just did. Now, you can come up with this law, and I am going to prove L'Hopital's rule. I just haven't looked at it yet, so don't worry. I'll get to that, back to that. But in general, if you have an integral of 1 over x to the n dx from 1 to infinity, if n is between 0 and 1, including 1, then the integral diverges. I guess that's what we probably should have said. The integral diverges. Instead, it's undefined. And if the exponent in the denominator is greater than 1, then it converges. And we've seen that through a number of examples, but you can generalize. And I think you have the same kind of expression if you integrate from 0 on the positive side to 1. If n is between 0 and 1, then it converges, and if if n is greater than 1 or equal to 1, then it diverges. So again, we just saw that in that one particular example, but you can generalize it to any expression like that. Okay, so I signed those last time. This is the chapter review problem. So these are due at the test, just to help you get some practice of doing all the types of integration that you need. Right, this is from a previous year, so ignore that because it's not the 24th. But most likely it will be just 8.2 through 8.5 for this particular test. I'm not guaranteeing that at this point, but most likely it will be, just because between integration for parts, trig integration, trig substitution, and partial fractions, those problems can take a long time. Therefore, I can't cover everything in one test. Okay, so let's do another one. This is we're integrating from 2 on the positive side to 4 of the function 2 divided by x times the square root of x squared minus 4. And so if you draw the curve, it looks like this. So it's one of the cases where the function goes to infinity at x equals 2. You can see that because the square root term goes to 0. So you divide by 0. Notice you can't have any values of the function between positive 2 and negative 2 because you'd end up with a negative square root. So the function is only defined at x greater than 2 or less than -2. But if we look at the area under the curve between 2 and 4, it's, there is an area. There's a function. There's an x-axis. The question is, does this function approach this asymptote quickly or not? How quickly does it approach it? We don't really know. We can't use our previous experience. We can't use this particular rule because it's not exactly in that form. So we're going to have to do the work. So what we'll do is we will take the limit as b goes to 2 from the positive side of the integral from b to 4 of 2 divided by x times the square root of x squared minus 4 dx. Now, what's the integral of that? Well, you might not recognize it, but if you take x times u times the square root of u squared minus a squared, that's the arc secant. So there is a rule. I didn't bring my book, so I don't have the actual integral to make sure I do it right. So let's search for it online. I think it's 1 over a times the arc secant of u over a, but there's something I just need to check. So what do we want to do here? Integral tables. So here it is right there. So it's the arc secant of x, but I'm pretty sure it's 1 over a. They don't have it exactly what I wanted. Let's see if we got another one here. Integrals table. What I'm looking for is the arc secant. Where is the arc secant? Yeah. Well, I'm pretty sure I know what it is. So if you go to the integral tables, what you'd find is that the integral of 1 over u times the square root of u squared minus a squared is equal to 1 over a times the arc secant of the absolute value of u over a plus c. So what we can do is we do the integral just by using the integral tables. So you get the limit as b goes to 2 from the positive side of, well, we've got this constant 2. So we'll take 2 times 1 over a. A is 2 because this is a squared. So you get 1 over 2 times the arc secant of x divided by 2, evaluated between b and 4. So we can cancel those out, and then we'll evaluate the integral by plugging in the upper limit. So we end up with the arc secant of 4 divided by 2 minus the arc secant of b divided by 2. And then we can take the limit as b goes to 2. So we can just plug in x equals 2 and see if it works, if we have a determinate result, which we do. So you get the arc secant of 2 minus the arc secant of 2 divided by 2. That's doing this, plugging that in there. So that's also the same as the arc cosine of 1/2 minus the arc cosine of 1. So the angle whose cosine is 1/2, so let's think about that. We could just use the inverse cosine, but let's think about this. So the x-coordinate is the cosine. So here's 1/2. That means that the angle is going to be pi over 3. And the angle whose cosine is 1, that is going to be equal to 0 because the x-coordinate where x is 1 is right here, which is an angle of 0 radians. So you get the final answer is pi over 3. So it does have a finite result, which means that this function, 2 divided by the square root of x times the square root of x squared minus 4, approaches the vertical asymptote at x equals 2 quick enough so that this area here, this little sliver of area, is small enough that it will give you a finite result. Okay. Now we did something like this the other day. I'm not going to redo it because I'm not going to put something that complicated on the test. So we'll just skip that for right now. And I've already assigned the homework, but if you weren't here Friday, there's the homework assignment. Let's see who else has come. So that's due next Friday, or this Friday, because I assigned it last Friday. So last night I was watching videos on how to deal with traffic circles in England. I was practicing my driving skills. The two things that I have the hardest time with traffic circles, are just so, there's a lot more traffic circles than stoplights in England, so you got to know how to deal with them. And I got I don't know if it was road rage. I did something wrong and this guy tailgated me, irritated me, and so I'm very sensitive about making mistakes when it comes to traffic circles. So if you've been to Roanoke, get off the exit there at Daleville, you've seen a traffic circle, which is an American traffic circle. They're kind of different in England. And watching the thing last night, I realized, well, it's kind of an interesting situation because I'm going to explain traffic circles to you here. Especially when you have a four-lane road going into a traffic circle. Okay, so chapter 9 is very different in what we're going to look at, and I'm going to kind of give you an idea of where we're going, because if we just start talking about sequences and series, you'll be thinking, what is this leading to? What does this have to do with calculus at all, or advanced math? So what we'll find out, probably about chapter 9, section 6, is that you can write the trig function, the sine of x, as 0 plus x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th divided by 6 factorial minus x to the 8th divided by 8 factorial, and then just continue on. So what this is called is a series. So we're going to talk about sequences first, but a series is a sequence. You take the terms of a sequence and you add them together. So the terms, each one of these things is a term in the series. And if we carry this out to an infinite number of terms, then you get an exact answer for the sine of x. Now, practically speaking, if you have something like a calculator which does algebra, and here it is, how does the calculator do the calculation, the sine of x in radians? Well, it probably does this. I don't design the computer, but I'm assuming it does something like that. And it does it out to a certain finite number of terms. It's not going to take an infinite number of terms because that would take forever. But what we'll find out is that each subsequent term is smaller than the previous term. And so, you can say after n number of terms that the original expression is accurate to 7 decimal places or 10 decimal places or whatever. Now, just like with the things that we're looking at in Section 8, the question is, does something diverge or converge? We had that general rule that the integral from 1 to infinity of 1 over x to the n dx converges for certain values of n and diverges for certain values of n. And what we need to do to be able to know whether this series converges or diverges is to have some kind of convergence criteria. So most of the first 5-6 sections will be talking about the convergence of series in general, and then we'll apply those rules to specific examples, which will include this particular, this will be one of them, but there's infinite series for the cosine, for e to the x, all the ones that are non-algebraic functions can be written as infinite series. Also, if you want to take the derivative, so this is another, there's two ways of coming up with the infinite series for the cosine of x. One is to use the methods for generating infinite series, which we'll cover in section 7 or 8. But another way would be to take the derivative. So if I take the derivative of the sine, I get the cosine. And so what I would get is, if I take the derivative of this, I'll get 2 times x over 2 factorial. And if I take the derivative of that, I'll get 4 times x cubed over 4 factorial. I take the derivative of that, I'll get 6x to the 5th over 6 factorial. And you can do that for all the terms. And if I simplify it, 2 factorial is 2, 2 divided by 2 factorial is 1, so I get x. Here, 4 factorial is 4 times 3 times 2 times 1, so I can cancel out the 4 factorials, 4 and the 4 factorial, and what that leaves is 3 factorial. So I get that if I simplify that expression, and then the 6 here cancels out with the first term in the factorial there, and I'll get x to the 5th over 5 factorial, etc., etc. Okay, so the reason I did that is just to show you anything we've learned in calculus relating to the integral or derivative polynomials, which we're really good at. You can relate those to the derivatives and integrals of non-polynomial functions through the infinite series. So there's anyway, there's a whole slew of new math. If you take differential equations, you'll use infinite series either to explain what you're doing or to solve the differential equations. So that's where we're going, but it takes a little while to get there. So let's, a sequence is just a listing of numbers separated by commas, and typically there's some pattern to them. So we've got n terms in this sequence. So a sub 1 is the first term, a sub 2 is the second term, a sub 3 is the third term, and so forth. And then you go up to the nth term. So you could just list a bunch of numbers and that would be a sequence. Or you could come up with an equation which would be, as a function of n, would give you the n terms in a sequence. Okay, so that's what it's, and you've had sequences before in other classes. So it's just a listing of numbers. Now the question is, what happens to the nth term of the sequence if it has an infinite number of terms? So we can look at, in this case, it's the limit of, it's not the limit of a function, but it's a limit of a sequence. So what this is asking is, what is the nth term of the sequence as n goes to infinity? And does that approach some value L, or does it diverge? Does it go to infinity? So let me just use a simple example. This one does not converge, but let's say we define a sub n is just equal to n. So if I wanted to write the sequence associated with that, a sub 1 would be 1, a sub 2 would be 2, a sub 3 would be 3, etc. And so if I said what is the limit of a sub n as n goes to infinity, well, the answer would be infinity. Okay, you'd say infinity, I guess. Or more likely you'd say it diverges. Just because, and I'm not adding them together here, I'm just saying, as I increase n, the value of the term in the sequence increases. And if I let n go to infinity, then it's just going to be infinity. What about something like 1 over n? So let's say a sub n equals 1 over n. So a sub 1 would be 1 over 1, a sub 2 would be 1 over 2, a sub 3 would be equal to 1 over 3. So what would be the limit of a sub n as n goes to infinity? Well, the answer would be 0, because ultimately you'd have, if I plugged infinity in there, I'd get 1 over infinity, which is 0. So that is an example. Okay. So how does the limit of a sequence compare to the limit of a function? Yeah, I mean, it's basically the same thing. You'll notice, so I'm going to ask you to pull out your calculators, because you have the ability to do sequences on your calculator. So yeah, what is this trying to tell you? It's telling you that the rules that we used for evaluating limits of functions, you can also use for evaluating the limits of sequences. Let me just give you an example of that. So let's say I have a function which is x divided by x plus 1, and I have a sequence a sub n which is equal to n over n plus 1. So all I'm doing is, one is a sequence and one is a function. What's the difference is that x can take on any value. It can be 1.6972. When you have a sequence, the values of n can only take on positive integers. And if I said what is the limit of f of x as x approaches infinity, this was from chapter 5, you'd say, well, let's say it's a rational function. The highest order terms are 1. They're both x to the first power, so I take the ratio of the leading coefficients. So I'd say it's 1 over 1 by taking the ratio of leading coefficients, and the answer would be 1. When you're doing a sequence, if I said what's the limit as n goes to infinity of n over n plus 1, the answer would be still 1 for the same reason. As n gets very large here, this 1 here becomes insignificant, so I'd have a million over a million and 1, and so a million over a million is going to be 1. Here, the same kind of deal happens, except with the function I can go to a million and 0.1, whereas with a sequence I can only go to a million and 1. Have to go in increments of 1. Okay, so now back to the calculator. Just to show you that your calculator does do sequences, and I'll show you the difference between what options they give you to kind of tell you the difference between the two. Yeah, okay. So if you go to mode, I don't know how they designed such a poor situation here. There's got to be some way of fixing this thing, engineering it so that it does better than it does. But you know, I don't use it enough to worry about it. Okay, so you'll there we go. Okay, so you got normal, scientific, and engineering. If you go down to the fourth line, you've got function, PAR, which is parametric equations. You've got POL, which is polar equation, and the last one is sequence. So choose sequence. So if you go to something like plot, so go to y equals, let me clear that. You'll see that you get a whole different kind of display. You've got n minimum, so that's a sequence starts at some value of n. In our cases, we've been let n equal 1. And then you put in the function. So if I put in 1 divided by, and you also notice that this button right here, can't see it now because there. Yeah, that button, it says x, t, theta, and n. So depending upon what mode you're in, that button stands for different things. When it's in sequence mode, it's n. So if I push that button, it'll put n down. So what that says is I want to show the sequence 1 over n starting at n equals 1. And then if I go to graph, I'll get that. And what you see is points. And the first point right here is 1 over 1. And the second point is 1 over 2. And the third point was 1 over 3, 1 over 4, 1 over 5, etc. So the difference between, if I did the function, so let's go back and change. You don't need to change it, but I'm going to change it. If I change to function, and then I go to graph, and if I do 1 divided by x instead of 1 over n, and I plot that, I get that. I get a continuous curve, because in a function, x can take on any value that makes sense. So the difference, so now I go back to mode, go down to sequence, and then graph, and I have 1 over n, which is equivalent to 1 over x, and I graph that. It looks the same. It's the same shape, except it's only got, 5 dots. One for x, n equals 1, 2, 3, 4, 5, 6. It's actually 6 dots. And you can see as the function, as the sequence gets larger in terms of n, that the value of the sequence approaches 0. Okay, so I'm going to turn that off. Put that back to the laptop. Okay. Let's let me just do one more example here. If I said a sub n is equal to 1 over n squared, then a sub 1 would be equal to 1 over 1 squared, a sub 2 would be equal to 1 over 2 squared, a sub 3 would be equal to 1 over 3 squared. So that's 1, a fourth, a ninth, etc. And if I said what's the limit of a sub n as n goes to infinity, the answer would be 0 still. It's the same as we looked at 1 over n. They both have a limit of 0. This sequence approaches 0 more quickly than 1 over n would do. So for sequence, the limit as far as the sequences doesn't make any difference. They both approach 0. 1 over n versus, the other one, like I said, was if I looked at a sub n as 1 over n, which you already did this, I'm just writing it so you can see it, we'd get 1, a half, a third, etc. And the limit would still be 0. Okay, now there's a squeeze theorem for sequences, and so let's say you have we'll say there's some sequence A sub n, and we'll say there's some sequence B sub n and some sequence C sub n. There are three some functions of n. And what we can say is that basically if A sub n is less than B sub n and B sub n is less than C sub n for all n, and the limit of A sub n as n approaches infinity equals L, and the limit of C sub n as n approaches infinity is equal to L, then the limit as n approaches infinity of B sub n is also L. So let me just show you what that kind of graphically what I'm talking about. If I plotted, kind of like I plotted here with the calculator. So I'm going to use different colors here. So let's use well, not use black because that's too boring. So we're going to make this one blue, this one red, this one green. So A sub n is going to be the smallest one. It's always, so let's say A sub n looks something like that. And C sub n, which one do I want next? C sub n is the green one. If C sub n looks something like this, and ultimately, if I went out far enough where they'd be almost exactly the same value, so they approach each other as n gets very large. So I'm only showing a couple terms here. So if I can evaluate the limit of this somehow, and I know that approaches L as n goes to infinity, and I can do the same thing for C sub n, for whatever reason, if these are easy to evaluate, but this one's not so easy to evaluate. But I know that the sequence B sub n is always between, has a value always between them. I know there's no way that the red curve can go anywhere else. It's going to be squeezed to the same value. So that's the concept. It's not geometric like we did with the squeeze theorem associated with limits. It's just more just visually looking at it and saying, well, I'm sure there's a mathematical proof, but we're just going to do it visually, that if the thing that's always bigger and the thing that's always smaller approach the same limit, then the one in the middle has to approach the same limit. That's the concept. Okay, so that's a squeeze theorem. There's also this absolute value theorem for a sequence. So it says if the limit as n goes to infinity of the absolute value of A sub n is equal to 0, then the limit as n goes to infinity of A sub n is equal to 0. And you might think, okay, give me an example of that. Well, let's say, and I'm just going to use kind of a, actually, I know what I'll do. Okay, I think I can. So let's say A sub n is equal to -1 to the n times 1 over n. So we know what this sequence looks like. It's 1, 1/2, 1/3, 1/4. We know that the limit of 1 over n as n goes to infinity is 0. Now this sequence, you would have A sub 1, which is -1 to the first power times 1 over n. So that would be 1 over 1. So plug in n equals 1 here and n equals 1 there. Negative 1 to the first power is negative 1, so you'd end up with negative 1. And a sub 2 would be negative 1 squared times 1 over 2, which is positive 1/2. And a sub 3 would be equal to negative 1 cubed times 1/3, which is going to be negative 1/3, etc. So we know the next term, a sub 4, is going to be equal to positive 1/4. And so if we take the absolute value of this, that gets rid of the first term, because the absolute value of anything means that it's always positive. So if I take the absolute value of a sub n, that's essentially equal to 1 over n. And that's because n is always positive. In sequences, n is always positive. So the absolute value of a sub n is 1 over n. It gets rid of that negative 1 to the n. It gets rid of the alternating nature of it. And what this theorem says, that if the limit of this equals 0, then the limit of that equals 0, which is pretty obvious. It's just, in this case, if we were to plot that sequence, it would look something like this. You know, we'd start off with the first point would be 1, the next one would be negative 1/2, then we'd have positive 1/3, negative 1/4, and you know, it bounces around, and it's still going to approach 0. It just instead of approaching 0 from one side, it approaches 0 from both sides. It's all alternating back and forth, but it doesn't affect the limit as far as the value of the sequence. You'll see where these come into play later. So that's the absolute value theorem for a sequence. Okay, what else have I got? Just trying to remember what I got here. Okay. Now there's a special case of sequences, and most of the ones we've looked at so far, except for this one, have been monotonic sequences. Monotonic just means that they change kind of gradually in one direction. So this one's bouncing back and forth. So this would not be a monotonic sequence. But things like 1 over n, even just n, would be a monotonic sequence. So I'm just going to give you some examples of some monotonic sequences. So these are examples. So a sub n equals 1 over n. Okay, just looks, we're decreasing in a nice regular pattern. So that's monotonic. What else? I mean, 1 over anything pretty much. 1 over n squared, 1 over n cubed. Even just if you did a sub n equals n over n plus 1. That would be monotonic too, just by looking at if you plug in values for n. So there's n, here's n over n plus 1. So you have 1, 2, 3, 4. So you'll have 1 divided by 1 plus 1, so that's a half. Then you get 1 over 1 plus 2, which is a third. And then you get 1 over 1 plus 3, which is a fourth, etc. 1 over 1 plus 4, which is a fifth. So if we were to plot that, you're going to get, say, 1/2 for n equals 1, and then you get a third, which is probably about there. And this one probably should have gone more quickly. Anyway, you can see they all have the same kind of behavior. They're either decreasing or increasing. So the third example will be an increasing one. So let's say, and this one actually approaches, and I just did that wrong, didn't I? Did I? Oh, yeah, I did that wrong. Sorry. Let's fix that. So you got 2 over, and that's 3. Sorry. So there you'd have 2 divided by 3. Here you'd have 3 divided by 4. Here you'd have 4 divided by 5. So it actually goes the other direction. Yep, that's right. Sorry. So here would be the first term would be a half. The second term would be 2/3. The third term would be 3/4. Fourth term would be 4/5. And it's going to approach 1. Well, you don't want to put a line in there. Okay, so that is still an example of a monotonic function, as long as it doesn't bounce back and forth. That's if it bounces, it oscillates in any form, it's not monotonic. But if it increases or decreases, but not one and the other, then that's monotonic. Okay. So we'll stop there for today, and we'll continue on tomorrow.